All right, our boundary condition, let's start, let's call this boundary condition here. This is 1. Let's call this boundary condition in temperature, boundary condition 2. No particular order there. So let's just start with boundary condition 1. All right, so, oops, partial. So we're going to take the partial now because we have t and x, or we have x and y back together. So now we have to start thinking about partial derivatives again. So we're going to take the partial derivative of temperature, the full temperature with respect to y, at y equals 0, right? That's our boundary condition. That has to equal 0. So let's take the derivative. So we have now still the sum of I equals 1 to infinity of what's the partial derivative of that expression? What's the partial derivative of a function of x with respect to y? Just that function back, right? So we have sine of lambda I x. Right? That doesn't change for the partial derivative. But then inside here we have C3I times sinh of lambda I times 0. Right? We're evaluating this at y equals 0. Plus C4 times cosh of lambda I times 0. Okay, this over here, cosh of 0 is 1, and sinh of 0 is 0. Okay, so what we're saying here is that the sum of sine times C4 is all equal to 0. So write that out. So this becomes the sum of I equals 1 to infinity of C4 times I, or C4I times lambda I times sine of lambda I times x. That's all equal to 0. Everybody see how we got there? Okay, so we've now enforced one of our two y boundary conditions. All right, and we still have this problem of I from 1 to infinity. So infinitely many constants, but we've improved our situation a little bit. Right, we went from 2 times infinity of constants to 1 infinity of constants. So extra impossible to impossible. Right. Okay, so let's now move on to the second boundary condition and enforce that. Oh, sorry, I'm not quite done yet, am I? So, okay, we still need to use this to solve for the constants, right? Okay, so this is just saying C4, sorry, just write this again. So this is saying C4, let's see, write this out, C4I is equal to 0. Why is that? That's a good question. Just make sure I got this right. Okay, well, my notes say at C4 I equals 0. I'm going to trust that for now. I'm having a hard time seeing that. Maybe one of you can see it. C4. Oh, yeah, okay. So what we're saying is this has to be true, right? This statement has to be true. C4 times some function of x has to be 0. Well, if we know that the function of x itself is not 0 everywhere, then the only thing that's left to force this is if C4 is equal to 0. Right? Hopefully that makes sense. So lambda we know is not equal to 0. That function's not equal to 0. It's a function of x. So the only thing that's left to keep this bound, to keep this true all the time is that C4I is equal to 0. Okay, yeah, question? Oh yeah, right, sorry. This should be up here, lambda I. Yeah, because you take the, right, so the chain rule. Sorry about that. Okay, so we stumbled through that one, but basically we got to the point where we're saying using this, we're eliminating one part of the coefficients. We're saying C4I, they're all equal to 0. Great. So that gives us back our new temperature expression, which is the sum from I equals 1 to infinity of C3I times cosh of lambda I y times sine of lambda I x. Okay. Now we have this, our new solution. This is coming out of enforcing this boundary condition. We can, instead of calling this C3I, let's just call this C, right, our unknown constants, CI now, just for the sake of making it a little easier. Okay, so we have this as our solution. Now let's enforce the second boundary condition. Okay, so the second boundary condition says temperature, which is the sum from I equals 1 to infinity. Get tired of writing this. So it's CI cosh of lambda IY times sine of lambda IX. Right, that has to equal what? What was our other boundary condition? That has to equal TH, right? And in fact, we want to evaluate this at y equals h. So let's take this and make this here. This is h, right? So lambda YH. Okay, so we now have this expression. So we have now enforced all of our boundary conditions, right? Both in the x and both in the y. And where are we left? We're left with infinitely many unknown constants. So maybe a little bit disheartening. What are we going to do? How are we going to go about solving for all of those unknown constants to get back the actual the constants for the temperature equation? Sorry, it's really not clear how to work with this now. So to deal with this, we have to recognize some unique property of the particular equations that we have in this system. Okay. So how many of you have heard of something called orthogonality? Some. Okay, you've probably heard of orthogonality in the context of, like, if you have two vectors, right? So let's say I have a vector, and that vector is, normal to a plane. If the vector is normal to the plane, it's orthogonal to the plane. Right? If I rotate that vector and I have another vector that's coming off that's at a right angle, it's orthogonal to that. The unique property of that is that if you take the dot product of those two vectors, say it's a three-dimensional vector, take the dot product of each of the three terms, or sum the product of each of the three components of that vector, it should be zero. Right? That's the definition of orthogonality. Is you take the dot product of two different vectors and you get zero. Now that same concept actually applies to functions, right? So instead of like a three-dimensional vector where you have basically three components, think of maybe a four-dimensional space or an n-dimensional space. If you can take the dot product in the n-dimensional space and that n-dimensional dot product equals zero, that n-dimensional system is orthogonal. For a function, it just means if I take one function, multiply it by another function, and then do the integral over some definite range, that's going to be zero if they're orthogonal. Okay, so it's almost like you're taking an infinitely dimensional vector, two infinitely dimensional vectors, taking the product of them, and that has to equal zero. Okay, so orthogonality is a weird, like, obscure concept, but it's really important in this setting because it allows us to solve for the coefficients of each of these equations. All right, so let's see. Here's the rule. So the orthogonality of eigenfunctions. So the orthogonality of eigenfunctions is defined as follows. So we take the integral over the homogeneous boundary condition 1 to the homogeneous boundary condition 2. Right? So for x, that would be what, 0 to w, something like that. I forget which one it was. So we're taking the integral of our first function. These are now orthogonal functions. Eigenfunction I, okay, we'll call it eigenfunction I, and then we're going to multiply that by eigenfunction j with respect to whatever the variable is that we're integrating. Right, so if those functions are orthogonal, we would expect 0, right? If I is not equal to j. I'll explain this in a second. And not equal to 0 if I is equal to I. Right, so that is confusing, but what am I saying? So I just told you that if you have two orthogonal functions and you take the product and then integrate them, you should get 0. So eigenfunctions have the unique property of being orthogonal, right? The eigenfunctions that we had were sines and cosines, but they're not just any sines and cosines, they're sines and cosines with different frequencies, right? You have this lambda term that's changing. So for each of the different lambdas, you have a different frequency of the sine or cosine. So that is an orthogonal function because you can multiply those functions together, integrate over the span or over the domain, and it will be 0. Right? If you don't believe me, let's look at these examples. Right? Here's an example. It's really hard to see. The blue line here shows if lambda I is 1. So this is the sine of pi over 2 w. Right, so you can see it's sort of following the sine profile. And we're integrating between 0 and 1. And then we're going to look at I equals 2 here, the orange line. So I equals 2 is now twice the frequency, right? If I multiply those two things together, I get the green line. If I integrate the green line, turns out I get 0. Okay? Interesting. All right, so now here we've got I equals 1 again, that blue line. And then I picked another random one, I equals 9. Okay, so now we have a really high frequency eigenfunction. Multiply those two together, the green line comes out. Integrate that from 0 to 1, we get 0. Interesting. Last thing is, what happens if I take the same thing and multiply it by itself? The same eigenfunction. So here's I equals 3, this orange. Orange and blue are overlaid here, right? So they're the same function. Square that function and you integrate, and now we get the green line. So green line is going from 0 and is always positive. So there's no way the integral of that is going to be 0. So if I have two orthogonal functions, the integral is 0. If you have the same function, you multiply it by itself, it's never going to be orthogonal to itself, right? A vector can't be orthogonal to itself. Okay, so we're using this concept now. We're going to employ this to basically get rid of part of the equation that is causing us problems and solve for the set of coefficients. All right, so for our example here, let's actually write this out. For our case, we have the integral from x equals 0 to w of what's our eigenfunction? Our eigenfunction we said was sine of lambda times x. Sine of lambda I times x, right? And then we multiply that by the eigenfunction again, sine of lambda j times x is equal to, right, it's 0 if I equals j, not 0 if, sorry to get that, if I is not equal to j. So 0 if I is not equal to j, not equal 0 if I is equal to j. Right, that's what we said. Okay, so the process here, what we're doing, and what you would do in your homework is, when we get to this point, you're going to go through, you'll find the eigenfunction. The eigenfunction is your function that has the property of orthogonality. So we're going to have to multiply through both sides of the equation by our eigenfunction, and it will sort of help. We'll see that next. Before I move on, any questions about the orthogonality part of it? Yeah. No, what we're saying is if I have a lambda that's subscripted, I'm just giving it a different subscript I versus j so that I could allow them to be two different lambda values. It has more to do with the lambdas and which lambdas we're picking than x or y.